Log on, tune in, find out. Another good idea from Cambridge.
Dr. Veselov from Loughborough University. We'll be talking on geometry in this.
So, yeah, we discussed with Rod whether it should be geometry of, geometry in, or geometry and basically what I'm going to present is not a review. It's just in a way several personal randomly selected points which I think show that that relation between geometry and discrete integrable systems indeed very deep, in the sense that it's the nature of integrability in many dynamical systems is just geometric, and that's what I want to say. Now, it's not new at all, and of course there are many people in the audience who know this very well, but let me start for people. I know that there are some people from parallel program who may be not aware of I think rather interesting development in discrete integrable systems which happened over last maybe 10 years. Now, let me start with, so there is a geometry and discrete integrable systems, right? I mean, so let me start with geometry first, and there is, I mean, if you take one of the first, I think, interesting theorems in elementary geometry, namely that medians intersect at one point, right? I mean, this is a kind of miracle. If you have three lines, they shouldn't intersect at one point, but here medians are concurrent. Means that they intersect at one point. Now, there is a generalization of this fact actually, which is if you have A, B, C, triangle A1, B1, C1, and then Ceva, Giovanni Ceva, Italian geometer of 17th century, so one is what, 1678 actually. There is a Ceva theorem which tells you that if you take a ratio ACC1B and then BA1, A1C and CB1, B1A, if it's 1, then this is exactly the same as concurrence. I mean, it's if and only if. Namely, if you take three lines, A1, BB1, CC1, then they intersect at one point, if and only if this ratio is product of this ratio is 1. Now, in fact, there is even he rediscovered even older result by Menelaus. And this goes back to the 1st century, Greek geometer, and he prove that if you take -1 instead of then here, then points A1, B1, C1 are collinear. B1, C1 collinear. So another miracle, if you take 3 points on the side of the triangle, then in general, of course, they do not belong to the same. This is A, B, C, A1, C1, and this is B1, and these are collinear even if the product is -1. Now, and this is a kind of remarkable fact, one of the beautiful results of elementary geometry. Now, what it has to do with integrability? Well, that was essentially, I think it was Boris Konopelchenko and Wolfgang Schiff who first pointed out this, but in a way, so there is a paper 2002 that basically say that this relation, if you take -1, this Menelaus theorem, is essentially nothing else but discrete Schwarz and KP equation. For this, you have to write it down in a slightly different form. So maybe I will write it here. So this is Menelaus theorem. The eraser here, okay? Just to write it down. So I will use Menelaus, that what -1, and then you have this discrete Schwarz and KP equation in the form phi12 in the usual 2, 3, phi 3 minus, so what is it, phi 3 minus phi13 divided by phi12 minus phi2. You write it down like this. Minus phi1. And this is equal to -1. I mean, you basically denote these points as phi1, phi2, phi12, and this interpret this as a shift in certain direction as we do in discrete system normally, and then you will have this, which is discrete Schwarz and KP equation. So in a way, Menelaus theorem is goes in the one of the probably most important discrete equation in dimension 3. Now, so this is a kind of example which is very well known in our community, but maybe not realized outside, that KP hierarchy, which appear now, I don't know, everywhere, including algebra, it's nothing else but discrete. Its discrete version is just Menelaus theorem in a way. Now, so this is the first. Now let me tell now the second story, and this story is so that was first story, and that's relation between. Now the third story is more interesting, mainly in 1992. Two independently appeared two very interesting observation has been done. I mean, approximately at the same time. So one is Richard Schwarz, and he considered so-called pentagram map, and Seva Adler invented a nice problem called recutting of polygons. Recutting of polygons, another dynamical system. Okay? So what is, so this is 1992. Now, so what is pentagram map, first of all? Let me explain this. So take pentagram. They started with pentagram. So, and very natural thing. You draw diagonal here. And you see another pentagram here. And then actually Schwarz started with observation which turned out to be known at least to John Conway. And then you can iterate in principle, and you can do it for any polygon. But because he started with pentagon, in pentagon case it's in a way not that interesting, but still, I mean that was so. So that's probably John Conway, right? I mean, who is one of his amazing observation. Well, but it may be going further. So you have P1, P2, P3, P4, P5. The claim is that this internal pentagon is actually projectively equivalent to the original one, right? So if you're working on the projective equivalence, it's actually, so, and moreover, P1 is P1 prime is here, so this is P5 prime, P4 prime, P3 prime, P2 prime. So John Conway said that P polygon pentagon, initial pentagon, is projectively equivalent to this pentagon. And of course, it's actually, this fact is not, it's just beautiful observation, it's simple. It's based on, so how to see this? So let me show just a little bit of geometry, at least. It's enough to prove, how to prove that two pentagons are equivalent projectively. So you can, you have at the point two diagonal and two sides. So you have 4 lines here. When you have 4 lines, then you can introduce double ratio. And double ratio is known to be projectively equivalent, projectively invariant of 4 lines passing through this. No, so how to define double ratio of 4 lines? You simply cross them by any line and take double ratio of these 4 points. And it's independent on the choice of line, right? I mean, that's projective equivalence. So, for example, double ratio of, at this point, for initial pentagon is double ratio of these 4 points. Now, let's look from this perspective. It's, you have this little pentagon and you have this little diagonal, right? If you look at this from this perspective, then this is up to permutation, which preserves actually the double ratio. This double ratio is of course the same as this double ratio, right? Double ratio of these 2 lines. But that's exactly equivalence, right? Proved. I mean, that, it's almost, you know, Greek proof when it was just C, right? I mean, that's what it is. Now, but anyway, it looks like nobody pay too much attention to this, but Richard Schwarz first observed this by algebraic calculation. Calculation were not trivial. And then he did the calculation. He didn't know that Conway already discovered this. He did the same calculation for hexagon. And he said that calculations are horrendous. The answer is the same. For hexagon, the same fact true, right? When he went further and discovered that it's not true, but that what he discovered is that dynamics is recurrent. You start from arbitrary polygon, you do this, what he called pentagram map, and he observed that you have a kind of recurrence, which is typical for integrable systems, of course, right? And it took quite a while, actually. There was Schwarz paper 2002, and then there was Ovsienko, Tabachnikov, Schwarz paper, I think a year ago. And Wolfgang Schiff, he gave a talk actually at Glasgow meeting in this program, satellite meeting, in April. So this is recent result, and you can see a PDF file of his talk in Glasgow for the details. It's amazing. This is nothing else but discrete Schwarz and Boussinesq, which is a reduction of this one. And his arguments are pretty similar to what you see here. Actually, it's not difficult at all in a way, but I mean, it must be again somebody from integrable community to see the relation with discrete Schwarz and Boussinesq. So this is one story. Now, parallel story is the following. So this is pentagrams, the story of pentagram map. And this, of course, explains many things, including recurrence. Now, recutting of polygons. That's so this is the following story. It's funny because Seva Adler also started with pentagon case some time ago, but he was inspired by different things. Namely, well, he was PhD student that time in 1992, and he was reading my review on integrable systems and wanted to have a model, a simple model, right, for himself to understand what integrable map is, and he invented this. I mean, I asked him why he considered this that time, because we didn't know that it's integrable. I can't see any relation with whatever with the integrable system we knew at that time. And he said that, well, his motivation was this transformation. So what is recutting? You cut triangle, and then you see made a symmetry and cut it and put it back, right? And this transformation, that's a recutting transformation, right? So this transformation is clearly have two geometric integrals, area and all the sides, actually, not only perimeter but all the sides. But it's not fixed, of course, polygon uniquely. Now, what in that case, history was much faster. I mean, it took 6, and he showed me that a nice picture. I mean, this recurrence also he observed. So you cut, you do this, and then you do this cut, you do again, and so on. And you can see, actually, I should even have some of his picture, which are quite nice. But anyway, you would probably, you have seen a lot of pictures of integrable dynamics, that's typical integrable dynamics, right? And the explanation came much faster than here. It took quite a while, but in Seva's case, he realized, well, it's 6 months. It's the same year actually, but it's published in 1993. So this was, but in that case was easier because at the same time we did the work with Shabbat on discrete dressing chain, which is a kind of discrete version of KDV, and he realized that this can be interpreted as a symmetry of dressing chain. So which is the same as, well, so this is a discrete KDV if you want story, right? So more or less. Anyway, so that's I mean this is two nice example of the following phenomena. If you think of something simple, with nice properties, with which is geometrically natural. And if it has nice property, then presumably you have a link with integrable systems. And that's what these two stories tell us, right? I mean, that's so. Now let me tell you now what I'm thinking about myself in this discrete. What I'm interested in this discrete business, and again, it turned out to be related with geometry, and this is and there is a link actually with this. The first example one of the first example came from other, and this is Young-Baxter map. So, what is Young-Baxter maps? You say you have a set X, and you have a map of Cartesian product of X by itself into itself, and it satisfies. It's called Young-Baxter map if it satisfies the Young-Baxter relation. So let me explain. So this is Young-Baxter relation. So this is also the Young-Baxter map satisfying Young-Baxter relation, also called set theoretical solution of the Young-Baxter relation by natural reason. And the story goes back to Drinfeld, and maybe the first person who in integrable community looked at them was Zhenya Sklyanin a few years before, but they have different motivation. But after Volodya Drinfeld paper where he mentioned this problem among, for some reason, quantum group, open problem related to quantum groups, this becomes a popular object among algebraists, and there are very interesting results in this area. But because their motivation are different, the geometric link is weaker in this case. But anyway, so this is Young-Baxter map is the same as set theoretical solution of the Young-Baxter equation, except by itself it's not integrability yet. I mean, it's not enough for integrability. So let me draw the standard picture. So what is that? Maybe I should draw like this. Yes. 1, 2, 3. You have, and this is triangle equation. 1, 2, 3. Okay. So right. So you can think of this as x as internal parameter of solitons, for example, and that's where, well, Young-Baxter equation appeared in integrable models of statistical mechanics in Baxter case, and for Young it was quantum theory. But you can think of this as, so for example here you have 3 particles, and they these are parameters of this particle. Think of polarization, for example, like for matrix soliton. And the outcome is different polarization. That's what happens with matrix solitons, for example. And then you have this property, which means that the result of interaction is independent of the order of interaction, because when you basically, here you have second and third particle interacting, and here it's first and second, and so on. So this has very natural interpretation, and then now it's not enough for integrability, and that's what I actually tried to explain in Glasgow. that you have to add Young-Baxter property is not integrability yet, probably. I mean, I don't know. You need to add so-called physicists call it unitarity. It's irreversibility in a way. I mean, this is identity, and diagrammatically this is like this. So if you have 2, and if you do this, then it's the same as this. Then it's the same, something like this. And then if you have these 2 properties, then it's then you can the basic fact is that these 2 properties implies that transfer maps. You can define transfer maps, and these are the following. So let me draw this diagrammatically again. So you take ith particle, and it's interacting with I plus 1, I plus 2, and so on. And the indices are modulo n. Well, so I plus n minus 1. So these are TIs. So this is Ti and what is n. N is fixed. Is a number of solitons in a way. So you have this TIN is the product, something like this. Maybe it's the other way around. Then you and I equal to 1 till n. So you have, and the transform commute. That's the main thing. TIN, TJN, and this is TJN, TIN. They commute as a map. So the TIN maps x to the power n into itself, right? And you have n maps, and they commute. So this is the main thing. And therefore, it's a kind of, so we have a, and this is a kind of integrability. I mean, if a existence of commuting maps is, so somehow it's very, so if you have Young-Baxter map, then you automatically produce a hierarchy of commuting maps, which we will call transfer dynamics, and for all n. So you have for all n, right? So now let me give an example. So let's look at the example, and this is Adler map. So R, and this is x, y, maps to UV. Now this is slightly modified. I mean, it's simplified maybe. It's modified version of this, but I mean it's essentially the same. Where U is, what is that? Y minus alpha minus beta, x plus y. V is x minus beta minus alpha, x plus y. So this is now, and Adler map is recutting. I mean, more or less. It's not quite. It's recutting. It's involution, and then okay. So this is Young-Baxter property is it looks like new. Of course, you never know whether it's new geometric theorem, right? Namely, so if you so you can, this R, corresponds to the fact that you do this and then you do that, and you do it, for example, you can put everything to the left, and then certain composition of geometric maps, which is composition of recurrence, give you identity. This is not obvious at all, right? I mean, and you can think of this as another theorem. I mean, which probably was not known, but the more interesting fact is that if you consider transfer dynamics, then this is the same as KdV dynamics on finite gap potentials, or this is linear on hyperelliptic Jacobians. And this goes back to Novikov's work on stationary solution for KdV equation, and that's actually was motivation for us with Shabbat, because these polygons, the picture of polygons, it's you can think of this as Darboux transformation, and actually, because Darboux transformation is you can think of this as a shift on hyperelliptic Jacobian. This is the closed polygon, means that you have a closed sequence of Darboux transformation, right? And that's what periodic dressing chain is exactly. Now, so in a way, I mean, and that's very nice. So if you don't care about KdV, if you don't care about spectral theory and finite gapness, which was a beautiful discovery, but anyway, it's everything is there. I mean, in this simple, you will, if you want to integrate this, you will have to recover all this, right? There is no chance, because everything is hidden there, right? I mean, just in this simple question, right? I mean, it's so the solution is okay. So this is now let me talk that, and that's the last. What we thinking at the moment. I mean, by we Vasilis Papageorgiou, Eurosouris, and Tassos Tongas, we're looking at the case of quadri-rational. I mean, that's so this is quadri-rational maps. Quadri-rational Young-Baxter maps. Okay. So there is a remarkable paper by Adler, Babenko, and Souris on this. This is 2004, and this is the following case. So X, we're talking about Young-Baxter maps. They classify it up to certain group. Now, X equal to projective line in that case, and if you have so quadri-rational is the following. You have X, Y, U, V here, right? And so this is R, right? And they basically said, well, if you don't have error here, then it's you can look from this, and this is what they call companion map. So companion map is YU map to XV, right? And quadri-rational means that both R and companion map are birational. And actually, what they did, they classified all these quadri-rational maps. Now let me draw it here. Now, so classification is basically in generic case. Generic case is given by the following construction. So you have and that's a beautiful result. You have two quadrics, Q1, Q2, on the projective plane, and the map is very simple. Just draw the straight line. If you have x and y, 2 points on a quadric, one on x Q1, let it be, and this is Q2, x on Q1, for example, 1 on Q2, you draw the line. Because it's quadric, you have two more intersection and point in general. And these are exactly, this is V and this is U. Now, because each of these quadric is CP1, this gives you quadri-rational map, and they showed that this map is satisfy actually Young-Baxter relation, right? And this is called F1 case. And basically, and they have so let me, yeah, okay. And they have this. So basically, this classification is the generic case called F1, and then there is a case when 2 points collide. That's F2, and then you have 2 double points, and that's F3, and then you have triple tangency, so that they intersect at 1 point. So this is triple tangency F4, and then there is a fourth order tangency. This is F5. Now let me look at F5, and then you will see what is. There is a little problem here. So this classification of quadri-rational map is absolutely correct, but when you consider corresponding, the problem is modulo which group you classify. Yes? No. I mean, this is a map already. I mean, you have the map is you just take this, for example, and you cross this. So yes, you have singularity. No, you're absolutely right. I mean, that's the key thing. That's the key thing. I mean, this is a birational map. It has 4 singular points. When you blow up, and these 4 points, there are 4 points also here, and you can order them in such a way that you can point out exactly what is the image of this point, and you know, all this is done in ABS.
So is it just birational, so the two, or is it all from
Sorry?
You wanted to say by rational given
Degree, yeah, I mean, okay, maybe I should write the formula. U is, well, it's that's probably the answer to your question. A of yx plus b of y, c of yx plus d of y. That's a general thing, the general, and this is a of yx plus similar. Maybe it makes sense to draw it anyway. And degree of all these polynomial are less or equal than 2. Right. Now, you're absolutely right. I mean, this is generic case, and this is, I should say, maybe it's 2, 2. When both degree are 2 in quadratic in y. So that's now what I want to say. Yes. So let's look at the example. Let's look at F5. In that case, 2 quadrics has the following form. You have, let's introduce here coordinates W and Z, for example, and you have 2 parabolas. So Q1 is W is Z squared plus alpha, and Q2 is W is Z squared plus beta, right? That's exactly type 2, they tangent at infinity, right? There is only one common point at infinity. And then you take this construction, and then you have here X, Y, and here V, here is U. Right. So, and that's if it is X, and they uniquely, of course, have the unipressure. So this is Y, the coordinates of X capital and Y capital, X and Y, and similarly here it's V and U. And easy calculations show that U equal to Y plus alpha minus beta, X minus Y. V is X plus alpha minus beta, X minus Y. Now, if you compare with Adler map, it looks very similar, except that it's actually, so there is a change, but but this is not conjugation. So this is not Adler map. But it's also satisfy Young-Baxter relation, right? So now, if you change here U to minus U and Y to minus Y, which is not a conjugation, which is not a proper conjugation. Okay, then clearly, if you change U and Y, then it doesn't change here. Now here it will be plus. Here it will be plus, and that will be exactly the thing. So then F5 goes with what we call H5. I mean, it's actually, there is another example we have which is related to F1. It turned out that you also have another Young-Baxter map, which is approximately related to F1 in a similar way, And this H1 is appeared actually first in integrable system in relation with general relativity, so it's called Harrison map, and I think it was derived first by Tassas, Tongas, and Tsoubelis and Tongas. So there is a parallel actually, and the explanation is very simple of this extra. If you so this is conjugation in ABAS sense, it's a proper conjugation, but in Young-Baxter you have to be more restrictive, right? And the main question here is how different actually. So main question which we would like to understand at the moment with Vasilis and others is that how different actually. I mean, it's how different are F and H families. I mean, it's, for example, if you take F5 and H5, if we take H5, then it's Adler, and we know everything. We have this KdV dynamics. F5, I mean, it has to be done. It may be, I mean, there is a little chance that it could be equivalent, but I mean, I doubt so. As a maps, as a Young-Baxter map, they are not. I mean, they're not. But maybe they're equivalent in a wider sense. So this is, now let me explain what's going on singularity level. I mean, in singularity, if you look at these quadri-rational maps, there are singularity, these 4 points. And for their choice, for F family, all these points are, I mean, the points here and the points here are exactly the same. Now, in this H family, you can actually swap them. I mean, it's exactly the same set, but it's different ordering. So dynamics on this singularity set is different. But because it must be projective transformation, you have essentially only one choice. It's just 1, 2, 3, 4. Klein permutation. You have to preserve double ratio. And so the explanation of this additional symmetry is pure geometric. Now, how essential this for the Young-Baxter map, and what this additional H maps means is what we trying to understand now. That's it.
Maybe you need a frame, like in the covalescent case. Maybe it's a double cover of your hyperelliptic curve.
I think it's again hyperelliptic story, but it's the L operator is pretty similar, of course, because there is the beauty of Young-Baxter map is that you can read off Lux matrix immediately from the map. So you have Lux matrix immediately. So, and then you can take monodromy matrix, and then you can take spectral curve, and this is again hyperelliptic, right? So we know that it's hyperelliptic, but what I don't know. I mean, it's still I can't see what's going on at the moment. It's kind of interesting question, but it's hyperelliptic for the equivalent again.
Do you assume a unitarity condition in this classification of the Young-Baxter maps?
No, but the thing is that what they actually, it has been classified there.
Yeah.
It's quadri-rational map modulo MEOP4. You see, and this is not, and that's, so in that case, and then they basically made a choice in the orbit of MEOP4, which amazingly satisfy Young-Baxter equation. And actually the explanation is that because they have chosen singularity set to be the same, it's very strong condition. And actually, Young-Baxter property is basically confinement. Singularity set must be the same, but it can be reordered, basically. This reordering is behind this H family, right? Now, so at the moment we would like to understand, you know, so this is basically what the classification is. They classified me for chosen one particular orbit, which turned out to be both unitary and Young-Baxter. And we're just trying to see if we're not missing anything, because we have to work MEP 2. And that's a bit delicate. Equivalence is a little bit more certain. And
the recutting of polygons.
yes.
May I ask you something, maybe to put back the continuity in the discrete? So these people who study moduli spaces of curves with graphs,
Yes.
To move around in moduli space, they cut a geodesic and then
Yes.
they twist it a little bit and then they reglue it.
Yes.
So it looks like yours is a discrete version of that. And you have KDV, you have discrete KDV, and those guys have KDV. So maybe
You are, well, I mean, the relation which I didn't mention here, and which is approximately in the same area, I mean, there is a cluster also business, right? Which is cluster algebras, you know this. And what you say is this, what is it? Teichmuller spaces.
Yeah.
It looks similar, but I think it's different. I think it is different. I mean, this recutting business. There is another map which is maybe more relevant to what you said, and this is if you can, instead of doing this, you can do this basically, right? I mean, you can something like this, and this might be, they're not equivalent, but that maybe could be relevant. But anyway, there are variations here which are not equivalent in these things. So maybe there is one, but I think recutting itself is not.
Any further questions?